if you have an infinite collection of sets, so you have an infinite number of sets, then the union, the notation for the union is going to be like a big U. It's almost like a summation sign from n equal 1 to infinity of the ANs is going to be equal to the X's such that X is in AN for some N in the natural numbers. And then for the intersection of an infinite number of sets, is going to be the X's such that X is in AN. So if you can guess, if you're intersecting an infinite number of sets, it's going to be for all N in the natural numbers. So something like that. I'm not sure if we're going to get into these kind of sets too much in this course. Although, what might maybe think of an example off the top of my head. Let's say if you have the set defined this way. Let's say if you have a set AI is going to be the numbers, let's say 1 plus 1 over n. No, excuse me, 1 over I. Let me make that 1 over I. 1 plus 1 over I. Like that. Let's say if you have a set like this. Let's see. If you want to find the intersection, let's say if the intersection of all these sets from, let's say, I equal 1 to infinity, so in other words, these are going to be the numbers. Let's say, what is this going to be? This is going to be like 1 plus 1. Where I is like a natural number, and then 1 plus a half, 1 plus a third, 1 plus a fourth on to infinity. Let's see. Oh, no, I'm sorry. These would actually be separate sets, really, the way I've written it. So this would be, let's see. Let me see. Yeah, that's right. That'd be right. So it'd be like this. So, for example, so let me write this down here. Like, for example, A1 would be the set that would have 1 plus 1. Then A2 would be the set that would have 1 plus 1 plus 1 plus a half. A3 would have, 1 plus 1 half plus 1/3. So these all be separate sets, I guess, if we did something like this. I was just trying to sort of think of an example. So this would be 1 plus 1 plus 1/2 plus 1/3, 1 plus 1/4, etc. Yeah, like this. Now, yeah, so probably probably forget it like this. It probably looks something like this. So if you intersected all the possible, an infinite number of sets, um, let's see. Yeah, even this is a very good example. Yeah, I guess, yeah, the only thing that would be in all these sets would be 2. Ah, yeah, right, right, 1 plus 1, like that. Right. I was sort of thinking of trying to think of another example of one. In my case, probably getting off course a little bit, but that in my case, that's the notation that you use for that kind of stuff. Okay. So next thing I'll look at is Cartesian products. And that's the next thing, Cartesian products. I don't know if you would have had this before or not, but it's just simply pretty straightforward. One point 1.5 definition. If A and B are non-empty sets, then the Cartesian product A cross B is the set of all ordered pairs and it's sort of written this way. A cross B is going to be equal. It usually has this notation for like a coordinate notation. We have like A, B, such that A is in capital A and B is in capital B. And an example here, if A is equal to 3, 6, and B is equal to 1, 2, 9, find A cross B. And solution. So again, you really just put together all the pairs. You can see just put 3. It doesn't really matter what order you put in, just get all the pairs. 3 and 1, 3 and 2, 3 and 9, 6 and 1, 6 and 2, 6 and 9, like that. It's just something we'll use a little bit later. And next thing we're going to do is look at functions, something you've done before. Just look at it maybe in a little more abstract manner. This is 1.1.6 definition. And let A and B be sets. then a function from A to B is a set F of ordered pairs in A cross B, using that Cartesian thing, such that for each A in A, there exists a unique B in B with A, B in F. That's sort of a pretty complicated way to talk about a function. What it sort of is saying is, let's say if we could try to relate this to what we normally have. So let's say if we normally have a function, let's say we call this set, maybe we'll call this set down here. This would be like our A down here. And this would be like our B up here. So what it really is saying, instead of like the way we normally do, is talking about, like, let's say this point right here would be like, say, one of our A's and one of our B's, like that. And then so the things that are part of this set F are going to be all these pairs that we have along here. And that's what it's kind of trying to say in kind of an obtuse way. And then, so once again, just sort of continuing with the book's definition, then the set A of first elements of a function F is called the domain of F. And denoted by D of F. It's one way you can write it. The set of all second elements is called the range of F. Sometimes denoted R of F like that. And one thing that they note, and again, this is something you remember from functions in general, when you talk about the domain, you're always going to be able to put something from the domain in the function and get something out. But so in other words, no matter whatever you're calling your domain, you can always put in your function and get an answer. But you won't necessarily get everything that's in B. So as they mentioned in the book, note that the domain of F will be equal to the whole set A, but the range of F won't necessarily be all the values over here. In other words, let's say, for example, let's say if your domain started down, say your domain went from like here over, say, to here, let's say, and that was, this was your domain A here. Then you can, and if you're calling this B here, you're calling this whole thing B, you'll notice it won't necessarily get these values down here for B. So the range will usually be a subset of B. Now, I don't want to complicate things here. A lot of times in this case, they would call B the codomain because you're kind of mapping from A to B. And so you're taking something from the domain and then mapping it to something in the codomain. But the range are the actual values that you get. Any questions? No. And then also, another way to say this is you go from something, the function go F from A to, but this is maybe a little bit more common what we're used to. And finally, as a picture, sometimes in 2 dimensions, you might make it as a picture. As we said, if this is your domain A, you'll get everything from A. So this is your domain A. And you put in your function. And maybe this is your set B over here. So this is your whole set B, but you'll just get your range, like say your range of the function will be in here. And over here, the domain of the function will be over here. So it'll look sort of something like that. So now sometimes you will get all of B. So in other words, sometimes you'll take things here and you'll cover all of B, or in our case of our line, you'll get all the values here. And then we'll talk about in a few minutes. That's what's called the function. It's called onto if you map to every point in B. But we'll have that formally here pretty soon. Okay, let me do a few more things here. Okay, and now we're going to talk about direct and inverse images. So let F A to B be a function with domain equal to A, like we said before, and range so be like that. And then once again, do definition 1.1.7. E is a subset of A. Then the direct image of E under F is a subset FE of B given by FE equals, so it's going to be, so again, we're taking a bunch of points that are this E, this set E, and putting them into our function. And so therefore that's going to be the values of our function of X such that X is in E, like that. Which kind of makes sense. It's basically just saying, you know, if we did like a picture again, let's say you have like your set A here, you're going to just take some subset this time, E. You're not going to take all the points in your domain. You're going to map it over to here into B. And once again, you're going to get some of these. This is going to be your F of E here. Something like that. And that's, so this would be your function F, let's say. But now let's go back the other direction. So if H is a subset of B, then the inverse image of H under F is the subset H inverse, again, use a -1 for an inverse, H of A given by the X is in A such that F of X is in H. So that's sort of going backwards now. And so let's see if we interpret. In other words, what this is saying, again, H is a subset of B. So it's going to be like over here. So we have B, and we have like, say, some subset here, H. And so the inverse would be basically the points that this set H came from. In other words, what points of the function did these come from? What x's do you put in your function here to get to here? Because remember, the function going this way. And then so you're kind of looking back, trying to figure out, okay, what point did you put in over here? And that's going to be this F inverse image H, like that. sort of way to think about this, the sort of standard example would be x squared. That's what they use in the book. I'll use the same things. That may I'll just change the intervals a little bit. So let's say if we have this x squared, then
Sorry, for the one that you just did for the inverse image, would the line have the inverse up over it, or would it still be an
this here. Oh yes, actually, right. This would go this, and then actually, right, you could put one like maybe the inverse image would go like that, huh?
yeah, okay.
Yep, right. You'd probably do it either way. You'd probably still make this f this way if it's going this direction, then and or you could make the inverse that way. Yep, probably either way would be correct. So now, if we do this, and let's say if you have these two sets, x, or let's say you have a x is such that x goes from 6 to 8, and b x is such that this goes from this. So so what is f of a equal to? What is f minus 1 of b? What's that equal to? So yeah, let's start with this first of all. So is it pretty obvious what f of a would be?
Yeah. It's 7.
Pardon?
It's 7.
For, let's see.
It's, oh wait, x squared. It's not 7. It's 49.
Let's see. Yes. Now, what this is, though, this is going to be the whole interval, though. In other words, this is saying these would be like real numbers. So it could be everywhere like 6.1, 6.2, all the way up, right? These wouldn't necessarily be. So what this is saying, it's going to be this whole thing. So, and since this is going to be continuous, it's going to get, and this is like just this is just going to be like a graph, sort of something like this. So it's going to be continuous. So you probably just start at the bottom, which that's going to be 6 squared be 36, huh? So it's going to be, and you could write this either in set notation. I don't know. Maybe we just may just make it an interval. So it's going to go from like 36 to to like 64 because 8 squared would be 64. So maybe another way to, let's sort of like make a little graph of this here. So this is going to be a parabola, and then it's going to start at 6, and then it's going to go to 8. And then if we do 6 squared, it's going to be 36. And then up here, 8 squared would be 64. We have a visitor. And so since since it's a continuous function, then if we're going, and it's yes, since it's a continuous function, then if it's goes from, and it's also increasing, huh? Because it's always increasing. So if it's we have a 36 here and 64 here, and it's a continuous increasing, we're going to get everything in between, huh? So that's going to be something like that. Again, I'm not sure how you want to write these sets. I wrote this for something like it's not real important. I just wrote it this way. Does that make sense?
Yes.
Now, the other one's a little bit trickier. So the other one, let's say if we do the inverse of B, so the inverse image. So these are values here. So this time, what we're going to have is, so we have our function, and let's say it's going to look something like this. So once again, this is the inverse image. So we're working over here, and B is going to be from 4 to 16, like this. And so the question is, where did these come from on the x-axis?
So would that be like 2 and 4?
Mm-hmm. And
And everything.
oh yes, well right, that's what this would say, but what else could it be?
Oh, it could be negative 2.
Uh-huh. Yep.
I didn't think about that.
Yep. -2. And actually, I probably should write it the other way, huh? So it'd be -4. I'm getting kind of sloppy in the notation here, but you kind of get what I'm saying. So yeah, the union of 2 to 4 and -4 to 2. So let's go back to our f of a. So now, what if we took the inverse of f of a? Would we get back where we started? So, and that's what you would kind of expect, because we did f, then we're doing the inverse again. So let's think about that. So in other words, what's the inverse image of this up here?
6 and 8.
Mm-hmm. The interval 6 to 8. And
-6.
uh-huh.
Well, -8 and -8.
Uh-huh. -8 to -6. It's kind of interesting. So so in this case we have, in this case, f inverse f a is not equal to a, huh? We didn't get a back, we got something bigger. Because usually you would expect, because now it's interesting, if a would have, if we would have started with this, and if that would have been our original a, then when we did this, we would have got back to there, because this still would have given us, because if this would have been our original a, this still would have been our output,
Right.
wouldn't it? So if that would have been our original, then this would have been equal. But in this case, since this was our A up here, when we did the inverse image, we didn't get A back. We got something bigger. Just kind of interesting. And let's see, I'll do just one more definition here, and then that should be enough. Let's see, let me just do. And this is 1.19 definition. F goes A to B, be a function from A to B, so you have something like that. And then a function F is said to be injective and or that another definition for injective means one-to-one. If fx1 equals fx2 implies x1 is equal to x2. So that's a function that's one-to-one. And so, like, for example, in our last example, if we had fx squared notice that one's not one-to-one, huh?
Right.
Not one-to-one, not injective. And of course, you could pick any number of points. You can just pick one because f, let's say, of -2 was 4, right? And also same with 2 gives you 4 as well. So those two were equal. F -2, those two were equal, even though what's inside here were not equal. Because you said from the definition, if it truly is one-to-one or injective, if two things are equal, that means the values you put in had to be equal. Now, can you guess something like that? Do you think that that's one-to-one? Let's try to prove it. So let's try to use what we have up here. So let's try, so let's do f of x1 equals f of x2. So let's put those into our function. 3x1 plus 7, 3x2 plus 7. And then the 7 will cancel. The 3's cancel. Looks like it is, huh? That's okay. No, you have to sort of see this. Another thing you can do is, so is you can sort of think, I'll let you finish writing, but you can sort of think of it as being, uh, if there being an inverse function available. One thing you can think like, so in this one here, in the x squared case, we had something like this, which you could actually see all these any point here, you would see there was another point over here, so it wasn't 1 to 1. But over here, if we were to plot this, it might look, let's say if this is, it might look something like this. And do you remember in algebra, we had like the vertical line test for a function?
Yeah.
Well, this time it's a horizontal line test.
Oh,
So, so this one fails the horizontal line test. And this one passes the horizontal line test. Because you can put a horizontal line anywhere and you'll never cross it. Here you put it and you see it crosses in multiple places. So that's another way to test that it's 1 to 1. So this is not 1 to 1, this is 1 to 1. So there's a couple ways. This is kind of a more rigorous way to do it. And then, and if we tried to do this proof up here, let's say if we tried to do the same thing here, if we did like x1 squared equals x2 squared, then if we tried to prove it this way, when we try to take the square roots, remember when you take square roots, you get pluses and minuses. So you would probably end up with something, and it's kind of hard to prove that something's not 1 to 1. It's usually best just to find the point. But if you did try to prove it, if let's say if you thought something was 1 to 1, you tried to prove it, when you start taking the square roots here, you can see you get pluses and minuses. So maybe a minus x1 would be equal to x2, and then but two positives would be equal, etc. Okay, and let me do just two. Yes, relate this. So that was part A. Then B is a function is said to be surjective or onto. A surjective. It's, or onto. If, as I sort of mentioned briefly before, if f of A equals all of B, i.e. the range of f is equal to B. And then finally, if f is both surjective and injective, then f is said to be a bijection or bijective. So, So on to, once again, is the fact that you get all the values. In fact, actually, we'll talk about it a little bit more maybe next time. But you can see this one here, this function is probably onto as well because it continues from infinity to infinity. So you'll probably get all the values of b if you're calling b the real, the real numbers, and you'll get all of b. So therefore, it's going to be onto, and then again, if something is both those, then it's a bijection.